Biostat 6611, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Howdy do, Bio 6611. In this lecture, we're going to talk about simple linear regression with a simple application and how we make inference to actually draw statistical conclusions. We'll start with a brief refresher of some of the background of simple linear regression before tackling how we do inference for least squares estimators and test those significant associations. We'll then show an example of regression code in both R and SAS for our FEV dataset, and then walk through some questions we can address with this regression output. So let's start with that refresher. Recall, we are talking about and have been learning about simple linear regression, whose model we see here as y sub I equals the intercept beta naught plus our slope term beta 1 times the predictor x1 for the ith individual plus some error term epsilon I, where the I subscript 1 through n indexes the data pairs y sub I and x sub I for each person or observations, outcome, and predictor. This simple linear regression model only has a single explanatory variable x1. Now, we will discuss models that aren't simple and have more explanatory variables in the near future. Now, the assumptions we have for this are the existence, linearity, independence, homoscedasticity of our variances, and normality of the error term. So let's talk about how we can do inference on these least squares estimators. Under our assumptions, we know that our error terms are assumed to be normally distributed with mean 0 and a true value of sigma squared sub, we'll say e. We also know that our outcome conditioned on our predictor values is normally distributed based on our assumptions with a mean of y given our predictor or predictors x, and the variance is calculated as y given x. Now, this is because mu is allowed to change linearly with that explanatory variable, hence y given x. In other words, it is our regression framework of beta naught plus beta 1 times x. So if we assume the normality of our errors, again as we do at the top here where I just drew the square, then the least squares estimators beta naught hat and beta 1 hat will also be normally distributed. And this is because they're functions of independent, normally distributed random variables. And we won't dig too much into that here today, but I'll note that if you have access to a Casella and Berger textbook, you can look up corollary 4.6.10 for more information. Now, if we aren't able to assume that normality of the error terms, we have a few options. One, going back to that central limit theorem, if we have a large enough sample size, which we've discussed in that past lecture weeks ago, can be somewhat dependent on our context, we can note though that asymptotic normality could be assumed for our estimators. So shout out to the CLT for helping us still be able to use linear regression, even in the presence of concerns about our normality assumption. Now, if we're still concerned about that and we don't think we have a quote-unquote large enough sample size, we still can look at estimating this through bootstrap methods or Monte Carlo methods to do inference on things like confidence intervals and calculate potential significance. So how do we actually test for those significant associations then based on the theory we've developed throughout the course so far? So let's start off by pointing out that we're specifically looking to test if there is a linear association between the explanatory variable x in our simple linear regression model and the response or outcome variable y. This is essentially the same thing as testing if the slope is equal to 0 in the simple linear regression model. Hence, we can actually test the null hypothesis that our slope parameter beta 1 equals 0 versus the alternative hypothesis that it's equal to anything other than 0. Now, to actually conduct this test, we can use the fact that we can take a ratio, as we see down here below, of beta hat 1 divided by its standard error, which is a t-statistic and therefore is going to follow this t-distribution with n minus 2 degrees of freedom. As a brief tangent, you may wonder now why n minus 2 degrees of freedom versus n minus 1 as we've seen in some other contexts earlier in the semester. Well, in this case, we're estimating both the intercept, our beta naught hat value, and also the predictor of interest, that beta 1 hat value. Since we have two terms we have to estimate and we derive those parameters for, we're fixing two of our n degrees of freedom in place. Now, if we want to calculate a 95% confidence interval for the slope coefficient, we can note here that, for example, we have beta 1 hat, that estimate we have in the simple linear regression model. We'll then use the t-distribution to look up our 1 minus alpha over 2, and for a 95%, we will put in our 0.05 for alpha, and then we'll multiply that by that standard error we can calculate for beta 1 hat. Now, if we ultimately fail to reject H naught, that null hypothesis, it tends to mean one of three possible things. The first is that all of our assumptions are met and there was no actual association. The second piece is actually that maybe our linear assumptions were not necessarily met and there actually is not a linear association, but there might potentially be a different type of association some other regression model or transformation might be able to help detect. And the third possibility is we've made a type 2 error. We failed to detect a significant difference when it exists, and we're underpowered. So let's take a look at how we can run the simple linear regression model in both R and SAS and what the output looks like before using that to answer some questions. So in R, we'll read in our FEV dataset from the Rosner textbook here, and then we'll fit our simple linear regression model that we see on the screen here, where we have the true regression model denoted in our code comment here, and we're fitting it with our outcome variable FEV and our single predictor of age. We'll then see that taking a summary of this object on the following slide reveals the information for our linear regression model. For example, at the very top here, it reminds us of what specifically we asked to fit for the regression model. It does a nice summary of the residuals we have from our observations in the regression model, and then we have our coefficient table of estimates. And here's where we can see things like what our beta naught intercept value is estimated to be, our beta value for the slope for age in this model is estimated to be, along with p-values with respect to our t-statistic from this data set we've collected. There are also some additional summaries we see at the bottom that we'll discuss more throughout the semester. Now, in SAS, things are a little different. We'll assume we've already read in our data set. We see if we use then proc reg here, we have a model term where we specify somewhat similar to the R syntax, FEV and equals age here. With the SAS output, it'll actually give us some separate tables of output, one of which will be an analysis of variance or ANOVA table summarizing these parameters at the top. There's a table summarizing various quantities of interest that we will discuss more in the semester, as well as a very nicely formatted at the bottom parameter estimates table that closely matches the information from R's raw output on the previous slide. So take note of these parameter estimates from SAS or R because we'll be leveraging them and their corresponding standard errors to answer some questions on the following slides. So let's take a moment to walk through various types of questions we could ask based on this output and how we can address and answer them. So let's start with the most basic, perhaps. What is the actual fitted regression equation? And we see here we can denote FEV hat, our predicted FEV based on our data set and fitting this simple linear regression model, is our beta naught hat value plus beta 1 hat times age. So that 0.432 plus 0.222 times age. Just taking that information from that regression coefficient table and plugging it into this equation framework. Now we might want to actually interpret what beta naught and beta 1 actually imply based on our data. For example, we might ask, what is the interpretation of the slope parameter? Now we're going to be very strict here and very detailed with our definition, and you may generally see it be a little more relaxed. But here we're going to state that for every 1 year increase in age, between the ages of 3 and 19 being very explicit here, the FEV increases on average by 0.222 liters. Now, I put the comment on the slide here, but note we've restricted to the observed range of age values in our data set here, so we don't commit any accidental extrapolation to people less than 3 or older than 19. In practice, many times when you see results reported, they won't necessarily be this explicit to note the range or domains of the predictors in their interpretation, but here we just include it to be very explicit about what we can say about the relationship of age and FEV on this specific model. Now, we may also ask ourselves the question, what is the interpretation of the intercept in this model? And here we would say that when age is equal to 0 years, the average FEV is predicted to be 0.432 liters. Now, for this problem, it's actually neither scientifically meaningful and also is committing extrapolation outside the range of values. So it's not meaningful because measuring someone with an age of 0 implies right when they're born, and it's unlikely we would have adequate techniques to measure that. And also, our study doesn't include anyone that young anyway. So it's inappropriate in this case to really interpret the intercept. However, this general framework of when everything is set equal to 0, that is the average of the outcome we expect. We now may wish to ask the question, well, is there a significant linear relationship between our predictor of interest age and the outcome FEV? And the answer here from our regression table is yes. We can see here that if we calculate that t-statistic, again, that ratio of beta 1 hat divided by the standard error of beta 1 hat, right there, we see that that equals the 29.53 we saw on our regression coefficient output table in both R and SAS. For our purposes, we can note more explicitly that's going to be distributed as a t-distribution with 652 degrees of freedom. If we were to work on calculating a p-value ourselves or just take the information from the table, we note it's a very small p-value, less than 0.0001. Thus, we will reject that null hypothesis that beta 1 equals 0 and conclude that there is a significant linear relationship between age and FEV. Now, we also might want to calculate that 95% confidence interval for age so we can have a brief but complete interpretation of our model and its summary to describe the variability around our estimate. Here we can see that we just use our same framework we're somewhat familiar with, hopefully at this point, where we take our point estimate plus or minus our test statistic, or our statistic, calculated from our t-distribution to correspond to our desired level of confidence and degrees of freedom, and our standard error we have from our table. In this case, the degrees of freedom is large enough that it is fairly close to the z-statistic, or that standard normal value of 1.96 we commonly see when we're calculating the 95% confidence interval. And this corresponds to a 95% confidence interval for our slope coefficient of 0.207 to 0.237. In other words, translating that to a way we can share with people in words, we are 95% confident that FEV increases between 0.207 and 0.237 liters on average for every 1 year increase in age between the ages of 3 and 19, if we just want to be a little more explicit without extrapolating. We can also answer questions about prediction. For example, we might ask, what is the predicted value of FEV for an 11-year-old child? We can see here that we simply take our regression equation, plug in that age to our framework, do some number crunching, and we see that it's 2.874 liters on average. Another question we might ask, well, based on this model we fit, what's the predicted difference as someone gets older between maybe a 16-year-old child versus an 11-year-old child? And so here we see we can write this in a slightly different way for the expected FEV given someone is 16 minus the expected FEV given their age is equal to 11. And what we really see is that we can take this component here, plug it into our regression equation, similarly take our age 11 and plug it into the equation there, so we have 16 and 11 for those values. We can note them by actually doing the math. Our beta naught terms will cancel each other out, and we'll really be left with this difference of 16 minus 11, or 5 beta 1. So, based on this difference of the expectation, we can then plug into our 5 beta 1 hat that actual predicted value from our regression model and output, where we can predict that the difference between a 16 and an 11-year-old child will be 1.1102 liters. Now again, note just very briefly here, the way we framed this problem, we used the expectation, which is why we don't have any hats over any of our beta coefficients in that exact calculation. And so for a final example, what is the 95% confidence interval around that predicted difference between a 16 and an 11-year-old child we saw on the previous slide? So here we can see we have a pretty similar setup to what we had before. We're going to take now, instead of just beta 1, we'll take 5 times beta 1. We'll then take our value quantifying our uncertainty based on the degrees of freedom and our desired level of confidence. And we'll then take and calculate the standard error for something that is 5 times beta 1 hat. Now, what we can note here is, or refresh ourselves, there is the property of the standard error, where if we have some coefficient a and a random variable x, we can also rewrite this as a times the standard error of x, which is what we do here, where we take the 5 out and then plug in that standard error of beta 1 hat in the next line there. But crunching these numbers, we then see we have a 95% confidence interval around that difference of 1.037 to 1.184 liters. Or in other words, we are 95% confident that FEV increases between 1.037 and 1.184 liters on average for ages 11 to 16. Or, we didn't note this before, but for any actual 5-year age difference between the years of 3 and 19 that we included in our study or in our data set, because it is this linear relationship. So the difference from a 5 to 10-year-old is going to be identical to these calculations we've already done for an 11 to 16-year-old or a 12 to 17-year-old. And with that, we'll end this lecture set of an example of calculating and interpreting a simple linear regression model and calculating some of these confidence intervals and estimates for inference.